The Bootstrap Method, introduced by Bradley Efron in 1979, is a powerful statistical tool for estimating the distribution of a statistic through resampling with replacement. This method is invaluable when the theoretical sampling distribution is unknown, providing insights into estimator properties like variance and bias. Bootstrapping involves resampling with replacement, crucial for estimating standard errors, confidence intervals, and hypothesis testing. It's particularly useful when the theoretical sampling distribution is unknown. This method allows for robust statistical inference by creating multiple samples from the original data, enhancing the precision of estimates without adding new information. The Bootstrap method involves creating multiple samples from the original dataset to enhance the precision of statistical estimates. By resampling with replacement, it generates numerous artificial samples, allowing for better estimation of parameters like variance. However, it doesn't introduce new information to the data, maintaining the original dataset's inherent characteristics. Bootstrap samples are generated by sampling with replacement from the original dataset. This technique allows us to estimate population parameters by calculating statistics for each sample. By repeatedly resampling, we can assess the variability and precision of our estimates, providing a robust method for statistical inference. Consider a dataset of 6 observations: 2, 4, 6, 8, 10, 12. Generate bootstrap samples by sampling with replacement, like 6, 8, 2, 10, 12, 8. Calculate the mean for each sample, then construct confidence intervals. This approach provides an empirical distribution of the mean, useful for statistical inference without assuming a specific distribution. Bootstrapping offers a flexible alternative to traditional hypothesis testing by not assuming a specific distribution. Unlike conventional methods, it is less sensitive to violated assumptions, making it suitable for complex models. While traditional testing relies on theoretical distributions, bootstrapping uses empirical data, providing robust confidence intervals and hypothesis tests without stringent assumptions. Confidence intervals offer a range for unknown parameters based on sample data. A 95% confidence interval implies that 95% of such intervals will contain the true parameter. This concept is crucial in statistical inference, providing a measure of precision and reliability in estimates, especially when theoretical distributions are unknown or hard to compute. Bootstrapping offers several advantages. It's non-parametric, making it versatile across various data types. It provides accurate estimates even with small samples and is simple to implement. Additionally, it allows for internal validation, enhancing model reliability. These benefits make bootstrapping a powerful tool in statistical analysis, especially when traditional methods fall short. Bootstrapping, while versatile, has limitations. It's time-consuming and computationally intensive, requiring significant resources. Sometimes it's incompatible with certain data types, like spatial or time series data. Additionally, it can be prone to bias, potentially compromising accuracy. Despite these drawbacks, its applications in hypothesis testing, standard error estimation, and machine learning remain valuable. Bootstrapping is pivotal in hypothesis testing, standard error estimation, and machine learning. It enhances model evaluation through bagging, improving accuracy and robustness. By resampling data, it provides reliable estimates without strict distributional assumptions, making it invaluable across diverse fields. Its flexibility allows for effective application in complex data scenarios, ensuring robust statistical inferences. In economics, bootstrapping aids time series analysis and policy impact evaluation, offering robust insights without strict distribution assumptions. In medicine, it enhances survival analysis and diagnostic test evaluation, providing reliable estimates even with small sample sizes. These applications demonstrate bootstrapping's versatility in handling complex data and improving decision-making in diverse fields. In finance, bootstrapping aids in risk management by estimating value at risk and expected shortfall, crucial for non-normally distributed financial returns. It also enhances asset pricing models like capital asset pricing model. In environmental science, bootstrapping estimates uncertainties in climate models, improving reliability in climate change studies, such as sea level and temperature variations. In social sciences, bootstrapping aids in analyzing survey data, especially with complex sampling structures. In marketing, it's crucial for estimating customer lifetime value and enhancing A/B testing accuracy. These applications demonstrate bootstrapping's versatility in handling diverse data challenges, providing robust statistical insights where traditional methods may falter. The Bootstrap method is a versatile tool for statistical inference, accommodating various data types and improving utility. While computationally intensive, it efficiently enhances model validation and precision. Its adaptability makes it invaluable across fields, offering reliable insights without strict assumptions despite potential biases. This method remains a cornerstone in data analysis, bridging gaps where traditional methods fall short.